For the last few classes we have been discussing digital modulation techniques, and we will continue in this class the same topic. In the last few classes we have first discussed baseband representation of bandpass signals and similarly baseband representation of bandpass systems, and then we have discussed PAM modulation scheme, which is the simplest digital modulation technique. Then we have seen how to demodulate PAM modulated signal using matched filter. We have shown that matched filter is the optimum filter that gives us the highest SNR at the receiver. And we have also seen with examples that sampling at multiples of t seconds is the best thing to do. That is, those are the best instances to sample, that is because that will give us again maximum SNR. And in the last class we have discussed PSK modulation, that is phase shift keying, and we have also introduced the term constellation, which actually gives a pictorial representation of the signals that are transmitted. So, how to draw the constellation? We have seen that first we have to take two signals, not necessarily signals from the possible transmitted signals, but any two signals we have to have such that the energy of each of those, not necessarily two signals, but for the modulation schemes we have discussed so far, we need to have either only one or two signals. So, we have to take a few one or two signals such that all the transmitted signals can be expressed as linear combination of those signals. If there is, we need only one signal, then all the transmitted signals are just scaled versions of that single signal, and that is true for PAM constellation, and that is why we get one dimensional constellation for PAM. So, those points, if we draw the scalings, if the transmitted signal xmt is amt times am times phi t is that unit energy signal, then we draw that point am on real axis. Then we have for am for different m, that will give us the constellation. Those points on the real line is the constellation. Similarly, for PSK modulation scheme, we have seen that we have to have two signals. We cannot represent all the signals as scaled versions of single signal. So, we have to have two signals. One is cosine omega ct times pt, reasonably scaled, so that suitably scaled such that the energy is 1, that is root over 2 by EP times pt cos omega ct, and also root over 2 by EP pt sin omega ct. So, those two signals if we have, we can express all the transmitted signals in terms of those two signals as linear combinations. So, then if we want to draw a point xmt, we will first express it as a linear combination of the two signals phi 1t and phi 2t, that is we will express it as am phi 1t and bm phi 2t. Then we will draw the point am bm on two dimensional plane, am bm point, and that point is the representation of that particular signal xmt. Similarly, for different m we will get different points on the two dimensional plane. So, those points together is the constellation of the PSK signal set, and we have seen that for 4 PSK signal set, the points are basically these points. Eight PSK signal we have these points, 16 PSK signal we have this point, and so on. And we have also discussed how to increase the number of points in the PSK modulation scheme. So, if we want to keep the probability of error same, we have to increase the radius of the circle, that is we have to increase the energy that is transmitted, because we want to have the same distance, but we want more points on the circle. So, but if we don't want to increase the energy, we have to put more points on the same circle, and as a result the probability of error will increase because the distance between the points is decreasing. Okay. Now, we have said before that the energy of the signal is nothing but the square of this distance from 0 to that point, but we have not proved it. So, we will first quickly show that actually the distance, square of the distance gives us the energy of the signal. So, let us see. Suppose we have a signal xmt and it is represented as am phi 1 t plus bm phi 2 t. So, that the vector xm which we draw on the two-dimensional plane for this signal is, we will denote it by this, is basically am bm, right. Now, we have said that the energy of this signal is nothing but the square of the length from 0 to this vector. So, what is, let us compute the energy of this first. So, what is the energy of this signal? Energy of this signal is this is the energy. Now, using this you can see that this can be written as 0 to t, because at all other places it is, this signal is 0. Phi 1 square t plus bm square phi 2 square t plus 2 am bm phi 1 t phi 2 t dt. Okay. Now, this is am square bm square then plus 2 am bm phi 1 t phi 2 t dt. We are assuming real signals phi 1 t phi 2 t. If they are complex, we have to take mod this square mod phi 2 square, then phi 1 t phi 2 star t and so on. So, what is this quantity? We have said that phi 1 t and phi 2 t are orthogonal if this quantity is 0. So, and we have assumed that phi 1 t and phi 2 t are orthogonal to each other. So, this quantity is 0. So, what we have here is am square and times energy of phi 1 t, that is 1, plus bm square times energy of this signal, that is 1. So, we have am square plus bm square, and that is the square of the magnitude of the vector xm. Xm is this. What is the length of this vector from 0 to this distance? That is the length, that is root over am square plus bm square, and this energy is the square of that. So, this is this vector's length square, that can be written as xm, this length square. So, this is the square distance of xm from the origin. So, we have seen that these points actually, these, seeing what is the distance from 0 of these points, we can actually say what is the energy of the corresponding signals. So, energy of the signal is basically square of this distance. So, PSK, so this again gives us, tells us that PSK signals have equal energy. So, PSK signal is constant energy signal set, and PSK modulation is called the constant energy modulation scheme. Okay. Now, what is the distance between these 2 points? We have said that it will actually depend on this theta, and can we express it exactly? Let us see. The distance between the mth and nth point, let us say dmn, is basically the magnitude of xm minus xn. This is, we can compute it, but we will not go into that. You can verify it yourself, that it will be EP 1 minus cos 2 pi by m minus n half. So, this is actually dmn square. So, what is the minimum distance? It will be minimum for m and n consecutive, that is when m minus n is 1 or minus 1. So, that is m is suppose 2, that is second point and third point and fourth point, those will be the nearest. So, d mean will put in place of this 1, and d mean will be root over, sorry, this is half, so it is dmn. So, this will be root over EP 1 minus cos 2 pi by m. This is the minimum distance, and as you can see, this also tells us that if we increase m, capital M, this minimum distance will decrease, because if we increase capital M, that means this angle is smaller, and as this angle becomes smaller and smaller, this increases, cos of that value increases. So, as a result, this quantity decreases. So, as we increase m, this minimum distance decreases, and as we can also see that from the figure, we have to fit more points on the circle, then we have to put them closer, that is the only way. So, 8 PSK we will have smaller minimum distance than 4 PSK, 16 PSK we will have smaller minimum distance than 8 PSK, and so on. If we keep the radius of the circle same, if we increase the radius of the circle, then again we can have a higher minimum distance. Okay. So, we have seen for PSK modulation scheme that the constellation of the PSK modulation modulated signal is it lies on a circle, and now we will start another modulation technique called quadrature amplitude modulation. This can be said to be a joint modulation of 2 different pulses, 2 different carrier signals. PAM was just amplitude modulation of one particular carrier signal. This can be said to be joint modulation of 2 different carrier signals. Actually, PSK was also such a modulation technique, because it could be expressed as linear combination of 2 different carrier signals, sin omega ct cos pt and cos of omega ct pt, that is phi 1 t and phi 2 t. So, but that was a special case, all the points lied in the in a circle, and quadrature amplitude modulation is again a generalization where they need not lie on a circle. So, quadrature amplitude modulation or QAM in short. So, this can be considered as a joint amplitude modulation of 2 carrier signals, and this expression will immediately say the same thing. So previously for the PSK modulation also we have seen that the modulated signal was actually of this type, but there was some relation between AM and BM. AM was cos 2 pi by m capital M times small m, and BM was sin 2 pi by capital N times small m. So there was some relation. If I tell one, you can tell the other, but here this can be arbitrary. We can select those points in fact. So this can be also expressed as real part of AM plus JBM PT e to the power j 2 pi FCT, that is real. Okay. So here this is basically, this is the low pass equivalent. This representation is in terms of the low pass equivalent signal, and this low pass equivalent signal is expressed in Cartesian coordinate system, AM plus JBM times PT, but this can be also expressed in the polar form, and that is, let us say, Vm is the magnitude, then e to the power j theta m is the phase, then Pt e to the power j 2 pi FCT. For PSK signal set, this Vm was constant. The magnitude of all the signals was same, whereas theta m varied. Here Vm and theta m both may be different for different m. So this can be written as Vm GT Vm PT cos 2 pi FCT plus j theta m, not j theta m. So this signal basically can be expressed in this form also. Okay. Now here obviously Vm is the magnitude of AM plus JBM, and theta m is the phase. So this can also be said to be a joint or combined amplitude and phase modulation. Like we can say that it is a joint amplitude modulation scheme. It is modulating two carriers, whereas in the polar coordinate system we can also say that it is modulating the magnitude as well as the phase. So in the PSK modulation, it was only phase modulation, Vm was constant. Here we can vary Vm as well as theta m. So this is combined amplitude and phase modulation. So it can be viewed as joint amplitude modulation of two carrier signals, whereas it can be also viewed as joint amplitude and phase modulation of a carrier signal. Okay. So now let us draw the constellation. For some specific cases we will draw, but let us see how to do it. So here also, just like PSK, we can see that because XMT is expressed in this form, we can take the same basis, same fundamental signals phi 1t and phi 2t. So our phi 1t is just like before, 2 by EP PT cos 2 pi FCT, and phi 2t is root 2 by EP PT sin 2 pi FCT. Then we can say that any signal XMT is AM phi 1t plus BM phi 2t. Remember that for PSK signal sets, again phi AM and BM had some relation. AM was cos 2 pi by capital M times small m, and BM was sin 2 pi by capital M times small m, whereas here they need not have any relation. We can choose the points and then we can say that that is our QM modulation. So let us see some some typical constellations for QAM, typical QAM constellations. So suppose we want to have 8 points on the constellation. So one way to get 8 points is take 2 PSK. So one circle here and another circle here, and then say take 4 points here. It's like a shifted version of 4 PSK. So this is also in fact called a 4 PSK signal set. If you shift all the points on the circle by some constant phase, then that is also a PSK signal, because it is also changing the phase only. Then you take this extra point on a bigger circle. So this is 8 PM, 8 QM. So we can have different 8 QM modulations, different 8 QM signal set. We can choose the points this way, we can choose the points in another way, we can choose in many different ways. So let us say we want 16 points. We can have another circle, we can put 8 points on that. That is one way to get again 16 QM, but another a very standard signal set for 16 QAM is this. So this is phi 1t, this is phi 2t, and these are the points. So this is 16 QM, and this is a very popular 16 QM constellation, or other 16 QM constellations, though they can be used. This is the standard 16 QM constellation that is used in practice. So this distance you can change. This is symmetric, all these distances are same, but this it can be amplified. If you want to transmit more energy, you can scale the whole signal set and then transmit. So if you increase the energy, so that will increase the energy. If you want to have more distance will result in less probability of error, whereas it will also result in more transmitted energy. So you are compromising on transmitted energy to have less probability of error, that is better reliability. So this is 16 km constellation, and there are some other very standard constellations used. So using this constellation, if you want to transmit, then what do? We take this phi 1t, phi 2t, and suppose this is m equal to 0, 1, m equal to 2, m equal to 3, 4, 5, 6, 7, 8, I mean so on till 15, because there are 16 points. You simply do this way, that if you want to transmit say m equal to 3, so you can transmit 4 bits using this, because this is 16 QM, and suppose you want to transmit the third signal, that is this point. How do? You simply take this coordinate of this, that is AM, BM, and then multiply AM to phi 1t, multiply BM to phi 2t, and then add them and transmit. So another advantage of these modulation techniques is that you need not have signal generators for all these points separately. If you just have signal generators which generate phi 1t and phi 2t, there is one generator which generates phi 1t, another signal generator which generates phi 2t, then you multiply this signal with some AM, multiply this signal with BM, and add them and transmit. You need not have separate signal generators for each point. And moreover, if the phi 1t is like this and phi 2t is like this, you can have phi 2t from this itself by changing the phase. So this is further advantage of having this kind of signal set. Now let us draw other constellations which are also used in practice. 32 QM. So it looks like this. So you basically have 16 QM constellation first. Then we want to add 16 more points. So we add 4 points on each side. Then on this side 4 points, then on this side 4 points, then on that side 4 points. This is the 32 QM constellation. What is the boundary of this? Its boundary is like this. It is not a square constellation like 16 QM. It is also called cross constellation because it looks like a cross. So this is 32 QM constellation. Similarly, if you want to have 64 QM constellation, that is even easier. That will not be 32 cross constellation. One very easy constellation to with 16 points is 64. Sorry, 64 constellation is this. Eight times 8 is 64, 8 square. So on each dimension there will be 8 levels. So on this dimension there will be 8. So 1, 2, 3, 4. 1, 2, 3, 4. There will be 8 levels. On this also there will be 8 levels. 1, 2, 3, 4. 1, 2, 3, 4. So then you draw all the points like this. So this is 64 QM. There are 64 points because on each dimension there are 8 levels. So 8 times 8 is 64. So this is not a cross constellation. This is square constellation. So that is 64 QM constellation. And we can draw other constellations also. If we want, say, 128 QM constellation, we have to add more points. So again, we have to remember that these are not the only possible constellations for so many points. For 64 QAM, this is not the only possible constellation. There are other ways of selecting the points. This is just one of them. And similarly, 32 QAM also, this is just one of them. Okay. Now, so we have so far done in this class, we have seen that if you draw a constellation, then say this point, the energy of the corresponding signal for this point is nothing but the square of the distance from 0. So this distance square is the energy of the corresponding signal for this point. Then we have introduced another modulation technique called quadrature amplitude modulation. It is called quadrature amplitude modulation because we are doing combined amplitude modulation of two quadrature signals. One is cos, another is sine. There are two quadrature signals and we are doing combined amplitude modulation of both the signals. And this modulation can also be viewed as joint amplitude and phase modulation of a single carrier signal. If you represent simply this by in polar coordinate, then it becomes amplitude and phase. Every point has some amplitude and phase. So it is joint amplitude and phase modulation also. Okay. Now, from the next class onwards, we will introduce other modulation techniques. But before that, in this class, we will introduce some basic linear algebra, which will be used in the later classes, and which will also make the later classes easier to explain other modulation schemes also. So, we will quickly revise some of the linear algebra concepts. One is that first we will define some things. A field, it is this field is a algebraic structure. It is basically a set. This is like say set of real numbers R. Set of real numbers is denoted by R. Real numbers. Set of complex numbers is denoted by C. This type C. So these are fields. They have two operations, addition and multiplication. Then they have addition satisfies certain nice condition, multiplication satisfies certain nice conditions. So because of that, those conditions, this type of sets are called fields. So what are the conditions? Typical conditions like addition is commutative, multiplication is also commutative. Then there is negative element for every element. Then there is multiplicative inverse of every non-zero number in these fields, in these sets. So these properties, because these sets satisfy those properties, these sets are called fields. And most of the times we will deal with only these two fields, so we will not give other examples, although there are other examples. Okay. So then we will need vector space. A vector space is basically a vector space over R is again another set such that it again satisfies certain conditions. Another set with an operation. So the operation is called basically the addition of vectors. For example, Rn. What is Rn? It is basically the set of all n tuples of real numbers. So set of all n tuples like a0 to an minus 1 such that ai, each ai is in R, that is real numbers for all I. These ai's are real numbers, and then this is n tuple, this one n tuple. Take all such n tuples, that set is called R power n. And we can define addition in that set, in this set. How do we do addition? Addition of two vectors like this plus b0 bn minus 1 is simply defined as a0 plus b0 to an minus 1 plus bn minus 1. This is the addition of these two vectors. Remember, this addition and this addition are not same. This is real addition, this is the addition of two vectors. Addition of two vectors is defined in terms of addition of real numbers. Similarly, if we have complex numbers, C power n will be defined as n tuples of complex numbers. Similarly, you can define the vector addition in terms of the complex additions. Okay. This set is a vector space over R, and there is another thing we can do in this set, that is multiply by any real number. If we have one vector, we can multiply by another real number, one real number to this vector, and we will get another real vector in Rn. So this is called scalar multiplication. We are multiplying a vector by a scalar. Okay. So a vector space should have one addition. We should be able to add two vectors, and we should be able to multiply by a scalar, that is scalar multiplication. So we should be able to multiply a vector by a scalar and then get another vector. These two properties also should satisfy certain conditions. They are all natural conditions, like scalar multiplication of the addition is alpha times this vector plus this vector is nothing but alpha times this vector plus alpha times this vector. So all such certain natural conditions should be satisfied also by a vector space. Okay. So let us see some examples of vector spaces. This is one example. There are other examples also. So one special case of this, for example, take n equal to 2. What is R power 2? It is basically the two-dimensional vector space. You can represent the points these elements in R2 as points on a plane. So 1 0 is 1 2 tuple. So this R2 is basically all 2 tuples of real numbers. So 1 0 root 2 5, all these are points, all those are vectors in R2. You can multiply a vector by any real number. This is one vector, you will get, if you multiply by 2 you will get another vector, if you multiply by minus 3 you will get another vector, and so on. So you can multiply by scalar to any vector here. So this is one example. There are other examples which are not like this, and these will be useful for us, and that example is, let us take all functions, set of functions, take real functions of real numbers. So x is real and fx is also real. So fx is a function, and take all such functions. So set of all functions. So f is a function of a real number and its value is also a real number. Take this. So this is also a vector space. Now what should we have in a vector space? We should have addition of vectors. So the vectors here are functions. Now if you have two functions f1 x and f2x, their addition is also a function. So it is a vector in this vector space. So how do we do the addition? This plus, it is defined as, so it's f1 plus f2. This is a function. How do we define f1 plus f2 of x? It is f1x plus f2x. That is the way it is defined, this addition. Addition of two functions is defined this way. So each value is added. f1x value and f2x value are added to get the value of f1 plus f2 at x. And similarly, you can multiply by a real number to any function. So if you have a function f, alpha times f is also a function. That function at x, the value is nothing but alpha times the value of f at x. This is the way this scalar multiplication is defined. If you multiply by a scalar to a function, that means you multiply each value. That is the way scalar multiplication of function is defined. Okay. Similarly, we can take complex functions of real numbers. So x is still real, fx is complex. These particular examples will be useful for us because signals are nothing but functions. So set of all real signals, continuous time real signals, are basically all these functions, and so set of all real functions of real set of all real signals actually form a vector space, and similarly set of all complex signals of this kind form another vector space. So we can again add two functions, we can multiply by a complex number to any function, we will get another complex function. So this will also give us another vector space. Okay. Now we will define some more concepts. These are some examples of vector spaces. Now we will define some more concepts regarding vector space. Okay. Now if we have few vectors, let us say if we have a vector like this and a vector like this, we know that these two vectors have something special, and one special thing about these two vectors is that any other vector on this plane can be expressed as a linear combination of these two vectors. So any point here is, if it is x, y, then this is basically x times this vector plus y times this vector. So these two vectors, this vector then cannot be expressed as linear combination of just a scalar multiple of this vector. So that is one nice property, and we can see that that property is missing from these two vectors. If we take one vector this and another vector, let us say this. We can express one vector as a scalar multiple of another vector here. So, here these two vectors are not linearly independent. Similarly, we can take signals. If we have, say, one signal, this pulse, this is our f of x, and if we have another signal, this is g of x. We know that gx is nothing but a scalar multiple of fx. It is minus something times fx. So, these two vectors, these two functions are not linearly independent. Okay. So, these are some examples which actually will come to very good use in digital modulation, and other common examples of linearly independent vectors are like this, and we can have, in fact, on two dimensional plane we can have any two vectors which are not on a line. These two vectors are linearly independent. But if we take two vectors which are on the same line, this and this is on the same line, so these two vectors are not linearly independent, because one can be expressed as a linear combination of the other. Now, so we have introduced linearly independent vectors. If we have now this, so far all the examples were two vectors. We can have, in fact, more number of vectors. Suppose we have a collection of vectors. We will always deal with finite number of vectors in this course. So, suppose we have vector v1, vector v2, and so on till vector vn. These vectors, remember, can be signals also. All set of all signals is also a vector space. So, we can have n number of signals. So, there will be n number of vectors. So, these vectors are called linearly independent if none of them can be expressed as a linear combination of the others. So, we have seen in this case, for example, that this vector can be written as a linear combination of this vector, that is basically a scaling of this vector, whereas these two cannot be written that way. So, these are linearly independent. So, if these vectors are such that no vector here can be expressed as a linear combination of the other vectors, then this set of vectors will be called linearly independent. So, for example, take the three dimensional space. If we have, say, that is basically R3, set of all three tuples, you know that any point in the three dimensional space can be expressed as a three tuple, is a triple of real numbers. So, if we have, say, 1 0 0 0 1 0 and then 0 0 1, these 3 points, we know that none of them can be expressed as a linear combination of the others. So, these 3 points are linearly independent, whereas if you take 1 0 0 then 1 1 2 and then say 1.5 1 2, these are linearly dependent, because these 3 are linearly dependent because this vector can be expressed as a linear combination of these two. Similarly, this also can be expressed as a linear combination of these two. So, let us just write that. Let us see, 1 1 2, this vector is nothing but this vector 1.5 1 2 minus this vector, minus half times this vector. So this vector is linear combination of these two vectors. So this set of vectors is not linearly independent, they are linearly dependent. Okay. Now if we have a set of vectors such that they are linearly independent, now if we have, for example, like this one point here, this is a single point, it is non-zero point. So this is obviously linearly independent, but certainly this does not generate the whole space, whole plane, because this point cannot be written as a linear combination of just this vector. That means it cannot be expressed as a scaling of this vector. So there is something more we need to have some vectors such that they will generate all the vectors, but they will also be linearly independent. So this requires a generating set. So if V1, Vn are linear or is a set of vectors, this is called a generating set of the vector space V. If any vector V in this vector space can be expressed as a linear combination like this of these vectors. So if this set is such that any vector here can be expressed as a linear combination of these vectors, then this set of vectors will be called a generating set of this vector space. That means all the vectors in this vector space are generated by these vectors. So in we say that in different ways. We say that this vector is generated, this vector space is generated by these vectors, or these vectors generate this vector space. Now if we have if V1 to Vn are linearly independent and it generates V, then it is called a basis of V. So this is a new term again. So we have seen what is a linearly independent set of vectors. Just now we have also seen what is a generating set of a vector space, and then we have seen that we have defined a basis to be a set of vectors such that it is linearly independent as well as it generates the vector space. So let us see some examples. Suppose we take simply this vector. This is linearly independent but not generating set. Now let us take 3 points like this. This generates, because we can express any point in fact as linear combination of just these 2 points, because these two you can take linear combination, scale it down, scale it up, or scale this vector and then add them in such a way that you get this point. Any point can be obtained that way, but we cannot say that these are linearly independent, because this vector can be expressed as a linear combination of these two. It is simply like this. For example, it is, if we have so this is a scaled version of this, and this is just as it is. If we add these two, we get this. So this vector is a linear combination of these two vectors. So this set of vectors is not linearly independent. So this is generates V, but it's not linearly independent. Whereas if we take just these two vectors, let us say, then these two are linearly independent and it generates V. So this is a basis. So in this class we have defined a vector space. Particularly we have seen that set of all functions, that is set of all signals, real or complex, of real variables. Real variable is a vector space over real numbers or complex numbers respectively. And then we have introduced two notions. One is linearly independent vectors. A set of vectors is linearly independent if any vector in that set cannot be expressed as a linear combination of the other vectors. We have seen some examples which are linearly independent. We have seen some examples where the vectors are not linearly independent, they are linearly dependent. Then we have defined what is called a generating set of a vector space. It is a set of vectors such that any vector in the vector space can be expressed as a linear combination of these vectors. Then we say that that set of vectors generates the vector space V. We have seen examples of sets of vectors which generate the vector space, and we have also seen examples which do not generate the vector space. And then we have defined a basis to be a set of vectors which are linearly independent as well as it generates V. And we have seen just now examples of such sets which this set is a basis, it is linearly independent as well as a generating set of V. And we have also seen examples where the set of vectors generates V, but it is not linearly independent, so it is not a basis. And we have seen example of a set of vectors, this vector, single vector, which is linearly independent but is not a generating set of V, and so it is again not a basis. In the next class we will continue some more preliminary notions in linear algebra, and then again come back to modulation techniques in this, which is a central part of this course. Thank you.